What's up guys, welcome to another tutorial, and today's tutorial gonna be a very short one, quick one, and we're gonna do high velocity impact problem. So we're gonna have a square tube and we're gonna impact it on a rigid wall with a high velocity. So let's go and do the tube together, the square tube. Okay, there are many ways to do the meshing, and what I'm going to show now is only one of the ways, one of the methods. Okay, go to mesh, auto measure, sorry, not this one, shape measure, and I'm gonna do a 4-node shell. Okay, so the first point 0, 0, 0. Tap. The second point is 0.05, then 0, 0. Taps and then 0.05, 0.05, and then 0, and the last point is 0 space or comma 0.05 comma 0. Okay, in this tutorial we're trying to do our simulation in meters. So here I have 0.5 meters. Okay, I click. Okay, I have this grid. Can play with the mesh, and you all know that. Let's make it 5 and 5. Accept. Okay, so we've done from here. Now I can go to element generation and then shell, and then shell by edge drag. So I'm gonna drag these edges. So the thickness, let's say for now we make it 0.1, and the segments, let's say make it 10, and in the Z direction, so I click by edge, propagate 1, 2, 3, 4, and you see this is my tube so far. Let's say I want it to be longer, 0.5. Okay, this is my tube now. Let's say I want it to be even farther, so I make it 1 meter. So this is 1 meter, and I click on the front view. I see like this. Maybe I want to increase the number of the elements, so I can make it 20. Okay, maybe I'm still not satisfied. I can increase more and more. Make it 30, and let's say try to make it 50. Okay, so now I have one of the square tubes, then accept. Alright, so now I click on F2. The first one, I don't need it. I can delete it from here. Just go to assembly and then right click and delete, and I have this. Okay, so now instead of just doing the impact on this one, I will make another tube and try to connect it to this guy. So how to do that? I want to make another tube with the same dimensions, so I can just go here, transform, and then go to rotate. I want to rotate around the X axis, so I rotate around the X axis, and the rotation point is this one, and the angle is 90 degree. And if you rotate now, you see, sorry, you need to click on the part or the elements. We select the nodes by part. Now if you rotate, it will become like this, right? So to rotate and make new elements, you click on copy elements. Now you rotate minus in this way, then you click on accept. Okay, so you have this two parts or two tubes. Now what I want to do, I want to move this guy to the middle of this. So I can use translate and translate in the Z direction, and the distance is around 0.45. Click by part, not by part, sorry. Click by element and propagate. I click on this side already. Now these two guys, now I move in the Z direction. Now you can see it is almost in the middle, if it's not exactly in the middle already. Okay, so now click on accept. Okay, so we have this T shape, and we're gonna make a rigid wall in here, and this structure gonna hit the rigid wall. So how to make the rigid wall? You can make it either from create entity or create keyword. So I do it here, create keyword, select all, and then under rigid wall I can make a rigid wall planner, and then make a new ID. This is rigid wall. Okay, now I want everything to hit the rigid wall, meaning everything need to will contact with the rigid wall. So here I just make it 0, and if I want to exclude any nodes, I can make a node part and put it here. Okay, now birth and death times, when you want it to be active and when you want it to stop, we just leave it there. We don't play with it. Now this is the head and the tail of the vector that will define our rigid wall. Okay, so we want, let's say, the rigid wall to be here. I need to know the coordinate, but right now I don't know, so I assume this one is 0. So if this place is 0, meaning the tail will be 0, and then the head, let's say it will be 1. Then if we click on accept, now we cannot see anything. But I can click on draw. So if I click on draw, you can see this one is exactly there. So I just click on, I want to shift it a bit to the right. So the head or the tail should be, let's say, minus 0.05. Accept. Now it shifted this direction. Accept. Done. Alright. Now I want to define the thickness of this structure. I go to all, go to section, go to shell. Now shell section, here I make it 0.83, which is 5 over 6, and then the thickness I can make it, this is 10 cm, I'll make it 5 mm, or maybe this is too small. Yeah, should be fine, 5 mm. Then accept. Alright, now I defined the shell section, but I have not linked to this part. So I go to model, part, now section, accept. Now I linked it already. So now if I click on appear, click on tick and apply, you can see the part become thick, and this thickness is actually the thickness that I defined just now. Okay, now here this is the 5 mm or 0.005 meter. Okay, there are a few things that I want to highlight here. This one, this end lock, if I change this one, the thickness will be changed, meaning if I put 1 or if I put 0, if I put -1, depends on the thickness will be how it will be considered. If I put 0, meaning this one, the one I defined, is actually the mid section. So when I click on appear just now, it will become like half of the thickness from the side and half from the other side. Just let's show it while we discuss the things. Okay, you can see here it become fat. Okay, no body shaming. It will become thick from both sides. Let me see where I can. Okay, see, become thick. Okay, my graphic card is not working very fine, so that's why it's not showing nicely. Okay, let's go here. Isometric. Okay, see here it becomes thick from both sides. But now if I go here, go to keyword and shell again. Now let's say I put 1, accept. You see now the thickness actually goes from the inside. And if I put -1 and accept, you can see actually the thickness goes from outside. Here you can see here the thickness become from outside when I put the value of n log equal to -1. So I just put 0 as default. Okay, right, and this one I just make it mesh. Okay, now this part are not connected together, alright, because you can see these nodes and these nodes are not duplicated. So how we can fix these two? There are a few ways that you can fix. For example, if you go here, go duplicate node. This is the most easiest way you can do, is just like a click button. So if you click here, you see these nodes, it will be merged together. You click merge and you accept, then these nodes will be merged together. Here at this point we have nodes from this horizontal and this vertical, so it's duplicated and it is in the same location. So if I merge them together and then click accept, then it will be linked together. These two parts will be linked together through these nodes that we just merged together. But I don't want to do that right now. What I want to do is a bit different. I want to use what we call it create here Constrained Nodal Rigid Body. Okay, so here I need to click on the nodes that I want them to be fixed together. Here you can see it's a bit difficult to select from all sides. So what I can do, I click on here element tools and then blank. I just hide or blank the things that I don't want to see. So now you can see here. Okay, now I can see all the nodes that I want to fix together. This one also, I just hide all these things. I blank them. Okay, so now what I do is go to model, create nodal rigid body, and here create, and then just select on the nodes that I want to fix together. So I click by edge, have 1, 2, 3, 4, 5. Here also 1, 2, 3, 4, 5. 1, 2, 3, 4. Sorry, that was a mistake. I clicked by mistake. I can also click by edge and propagate all the selection. Okay, I clearly select all the outside, all the nodes that belong to the horizontal one. Now I want to select the one that is inside. We have 24 nodes. I click here, 26. Here also I want to click on this line, and then I want to click on this one and this one, the nodes over here, and I rotate this side. Now I click here and here. Now I click on apply. Now you can see they are fixed together. Then I go back to here, blank. I just unblank the guys that I just hide them. Alright, now I have this geometry, I have the rigid wall. Now I need to define the material. Since we are going for a high velocity, we need a material that take into consideration the stress or the strain rate sensitivity, and for that we can take or use the Johnson-Cook material model. So material number 15, this one, and then UID. Okay, so as I said, I'm using meter square. So the density kilogram per meter square will be 7850. The G is 59.62 Newton per meter square, meaning gigapascal, so it should be E power of 9. And then this one, the Young modulus 1.161 gigapascal, E power of 9. Poisson's ratio 0.35. A is 400 megapascal. B is 1.5 gigapascal. N is 0.4. C is 0.045. M 1.2. The melting temperature 1800. The room temperature 293. And this one, epsilon 0, is the reference strain rate, or the reference strain 0.001. And the heat capacity 452. And these are the properties of high ductility stainless steel, and it is called AL-6NX. I will put in the subscription where I took these values and what actually these values mean. I will link down, or I just put the titles of 2 or 3 papers related to the Johnson-Cook material model. Then accept. Now I can go to model here, go to part. Here I can make the material, this one Johnson-Cook. Okay, this is blue, part number 2. This one I just want to change it to number 1, so it become red. This is actually totally not necessary, but I just show you so that you know that you can do this trick. Okay, it's linked together. Now let's say this one, we call it square tube. and it is T-shaped square tube. Accept. Okay, now we are using shell, and the shell has a thickness of I think 5 millimeter. But if we were to use solid model or any solid model with a Johnson Cook material, it will not work like this. We need to define one more thing, which is we call it the equation of state. Let's go up here, equation of state, EOS, and we use the linear polynomial. And here equation of state for this T, 6 and X, and this all you put them as 0 except C1 you put it as the bulk modulus of your material, and in my case it's 178 e power of 9 because it is gigapascal. Except this is not necessary actually, but I'm just putting here because in case that you are using Johnson Cook with the solid material, and then after you do that, you link that you link that equation of state here. Okay, but now I'm using shell, so no need to use that. Again, I want to see my rigid wall. Okay, take some time. Show the rigid wall. Okay, this is the rigid wall. If you want to modify it, you can also modify it here. And you can see here the normal is going this direction, meaning the face of the rigid wall facing my guy here, so should be fine. Let's show none. Now I want to define the material. Sorry, I want to define the material, the velocity. Sorry, not the material, the velocity. So initial velocity generation in y, so it will be minus 100 meter per second, and the slave type is a part ID number 2, and this is the thing. Then accept. Alright, there is no need to define a contact between the part and the rigid wall. It's already defined as I explained, because we include all the nodes and we did not exclude anything. Alright, now we need contact between the parts itself. So we go to contact, automatic single surface or automatic general. So automatic single surface, can say self contact, and then sorry, just put 0. You can see here all parts ID are included for single surface contact. Then accept. Okay, take some time. Alright. Okay, so now we just define the output. Model, no, click on all. I can go where? Control. I just want the termination time. (10 milliseconds), which is actually I think more than enough because our velocity is high. And then database, where is that guy? D3 plot 0.00. This is means is 1 millisecond. Now let's say 0.01 millisecond. Accept. Okay. I think that's all what we need. we can add additional features like here, ASCII options. Okay, need to wait. Hopefully it doesn't hang on me. Okay, good. The default output 0.01. Enter. And what I want here is only one guy. Rigid wall forces. Okay, this is what all I want. Just make it smaller, should be fine. Then accept. And done. Okay, click on model, see what we define. Constrained. The constrained nodal rigid body is to link between these two guys, which is actually this this red web, like spider web. Contact is actually to define the contact between the part itself, because maybe this guy will bend and hit this one, so we need to define that one. Control is the termination time, 10 millisecond. Database, this is the output. This is the output frames. This is the output for the forces, the rigid wall forces. Equation of state, this is extra in case you are using Johnson Cook with solid material. Initial velocity generation is going in the negative y, should be fine. And part number 1. Then the rigid wall is defined. Planar, everything is defined and nothing is excluded. Section, shell, and our shell is 5 millimeter. Okay, I think that's all. So we click on save. Pause. Stop. I go here. YouTube. I've lost the impact. T square tube. Okay. Okay, I saved it. I open here. Browse where you save the guide. So this is the file, and I maximize the resources. So let's see if it is correct or we get anything missing. Okay, it says 2 minutes. That's good. So we don't need to wait for a long time. Close. So this is the results already out there. And then plot. Double click on that, and then you select whatever version of the software you have. Just wait. Now you can see the rigid wall is there. And this is the impact. Yeah. You see what happens here. Okay, we go to the history, and then we click on nodal analysis, or sorry, not this one, ASCII. We click on ASCII, rigid wall forces, and this is the wall, then you plot. Oh, you need to click which force. Let's say I want the Y force. Plot. and then here you have the Y forces. Okay. Now, since this is done, I want to add two more tweaks in the file. Here I call it CNRB, and here I call it spot weld. So now I copy this one, I put it here, and now I click here. What I'm going to do now, I'm going to replace the CNRB with spot weld and see if there is any difference in the result. So now I not click on F2, I click on the here blank, I hide the things that I don't want to see, like this. Okay, I have the CNRB here, you can see the web shape. So what I can do here, create, constrain, this guy I just delete it, and delete. Now I will try to link between both of them using a different method, which is generalized weld. So I create again the same way you select by edge. So I propagate this guy 1, this guy 2. Here we have two lines actually. One line belongs to the part that I just blank, and another line, another edge belongs to this visible part. Now I click here, then I click here, I click here. Sorry, here. Okay. Now I cancel the propagate. I click on this edge, this edge, this edge, and this edge. Okay, now apply. Okay, now you have the spot weld is fixed together. Now what I can do is I just save this one. What I like, what my practice is, when these things pop up, I just control and copy. So this one's already copied in my clipboard, so I save. Then when I want to run, I just paste here, or browse and then paste. Then here, and it's a small simulation, so I can maximize everything. Okay, while waiting for this, I want to open this, the old one here, this one with the CNRB. Then the new one has finished, so I run the new one with spot weld, and we see if there is any difference between the two simulations. So this one is the first one we did with the CNRB, and this one the second one with the spot weld. They look the same. You can see the forces, not history, SQ forces, SQ database, rigid wall. We load the file, we have only one wall, then click on the Y forces. So we have the maximum here 1.876. This one with the spot weld. This is with the nodal rigid body. We click on SQ options, rigid wall force, load, wall number 1, the Y force, and then we click here and we see this one 1.9194. As you can see, if you followed throughout from the beginning, the two models are exactly the same, but one of them we linked the two tubes with nodal rigid body, and it turns out it gives higher forces. We did not change the mass, we did not change the velocity, we just changed the way how we linked the two parts. And this is the other one. You can see what's happening with this guy now. Okay, I can do this. I can do this. Yeah, you can see here. This one 1.1, the 1.92 with the nodal rigid body, and this one 1.88. This one with the spot weld. And that's all for me this time. Thank you very much. If you like this video, just don't forget to like and subscribe for more videos in the future. Thank you very much, and see you next time. Bye bye and have a good day.